Hello, I'm Ryan Baker and this is Big Day in Education. This week we're going to give a case study in the use of classification with educational data. This study comes from a paper by San Pedro, me, Alex Bowers, and Neil Heffernan in the Proceedings of the International Conference on Educational Data Mining. If you're interested in learning more, I encourage you just to type this into Google and you'll be able to find this paper. Every paper ever published in the Educational Data Mining Conference and the Journal of Educational Data Mining is free and open access for anybody in the world forever. The research goal of this paper was, can we predict student college attendance based on student engagement and learning in middle school mathematics? Using fine-grained indicators distilled from the interactions within the educational software 5 years earlier. So in other words, 5 years before now, we're taking data from what kids did in their educational software in middle school math, and then fast forward 5 years, and we're seeing whether those indicators can predict who goes to college. So why would we want to do this? Well, we can infer engagement and learning in middle school within these kind of learning systems, which supports automated intervention. If we know what really matters in the long term, we can intervene on it, and we can also provide actionable info to teachers and school leaders, telling them not just whether kids are, for example, bored, but whether it matters and what the difference might mean for these kids' future. But which indicators of engagement and learning really matter? Can we find indicators of the students at risk that we can act on before a problem becomes critical? This was done in the context of the assessment system, which Neil Heffernan and Christina Heffernan have been leading the team that's been developing for about a decade. Assessments assesses as it assists, helping students learn math while formatively assessing them and providing that information to teachers and school leaders. The log data we had was data from a little over 3,000 students in 3 school districts in Massachusetts, 1 urban and 2 suburban. These students completed just under 500,000 math problems, working approximately 1 class period a week in the software for the entire year. These days, kids also use the assessment system as homework, but at this point it was primarily used in class. Within these about 500,000 math problems, the students made 2.1 million problem-solving attempts or hint requests in the assessment system. And this was done between 2004 and 2007. The dataset we had at hand had records not about just the use of the system, but also records about whether the student eventually attended college, obtained through collaboration with the National Student Clearinghouse. 58% of the students in the sample attended college. From the interaction data in the system, we had automated detectors, which had been applied to the data from assessments. These detectors had been previously developed using prediction modeling and were published in previous papers, including, and in particular, Pardos et al. 2013. Building a detector and using it in another analysis is called discovery with models. One of the detectors we had was a detector of student learning. In this case, we used Bayesian knowledge tracing, which is a classic algorithm for doing this, and we'll discuss this algorithm in detail later in the course. Great stuff. We also had detectors of student engagement, and I should point out that we didn't use any sensors for any of these detectors, just log files. No camera, no posture sensor, no GSR bracelet, no EEG pendant, no fMRI machine, nothing. The first detector we had is a detector of gaming a system, which is the intentional misuse of educational software. It includes things like systematic guessing. For example, if a student tries 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 38. That would be gaming the system. Another example of gaming would be rapid hint requests. Tell me the answer. Click, 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 hint, 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 answer. Hint, 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 answer. Another example would be off-task behavior, which is stopping work in educational software to do an unrelated task. This doesn't include talking to the teacher or another student about math. It only includes when the student's completely disengaged from the task. And these two things, pause because you're disengaged and pause because you're asking for help from the teacher, can be distinguished by the behavior before and after a pause. We'll talk about this actually a little later in the class. And carelessness, making errors despite knowing the skill. We also had affect detectors, and again, no sensors, just log files. Detectors of boredom, frustration, confusion, and engaged concentration. And for more detail on these detectors, again, see Pardos et al. 2013. The college attendance model. What we try to do is predict whether a student attended college from the student's year-long average of these behaviors according to the detectors. And what we used was a logistic regression classifier because we had binary data. Went to college, didn't go to college. This was cross-validated at the student level, which means that we built the model on some students and tested on other students, and we'll discuss this more next week. The first thing we did was look at the predictiveness of individual features in a logistic regression paradigm. So first we looked at whether the student knew the skill in the tutor and whether they got things correct. And you won't be surprised to learn that the more students got things correct in middle school, and the more they knew in middle school, the more likely they were to go to college 5 years later. Now, this is not shocking, but it's kind of nice to see, and it tells you that our approach isn't completely crazy. Also, it's nice to have these kind of things in the model because they interact with some of the engagement features, and we'll look at that in a couple minutes. Also, students who were bored more often were less likely to go to college, students who were confused more often were less likely to go to college, and students who were frequently in engaged concentration, flow, the feeling that kind of everything is dropping away and you're just totally focused on the learning task. How you feel right now watching my lecture, I hope. This was associated with going to college. If students were off task, no real relationship. Kids who are off task in the system more often were not more or less likely to go to college. This may sound surprising, but actually it replicates things that have been seen in other contexts as well. Gaming the system turned out to be the single strongest feature by itself. The more you game the system, the less likely you are to go to college. Carelessness, on the other hand, was positively associated with going to college, and we'll talk about this in a minute. And finally, the number of first actions in the system, the number of times a student started a problem, which is kind of a proxy for going to class because teachers give students problem sets that they're supposed to complete. This turned out to be fairly strongly associated. If you go to class more often and use the system more often, then you're more likely to go to college. Now let's look at the full model. This full model where we took all the features, put them all together, got an A prime of 0.686. We'll talk about A prime next week, but essentially a 68% chance that if you take a student who's not going to go to college and a student who is going to go to college, the model can tell which is which. And a kappa of 0.247, which means, we'll talk about this some more, that the model was about 24.7% better than base rate, which for the moment you can think of as better than chance. We'll talk about it more next week. The model was statistically significantly better than chance, no shock. And it predicted about 10 to 13% of the variance in who goes to college. The final model, when we drop out all of the non-significant features, indicates that college enrollment can be predicted by a function of student knowledge, student correctness in the system, how much the kid used the software, carelessness, confusion, and boredom. Interestingly, gaming the system, even though it was the single most predictive feature, doesn't remain significant when all these other things are in the model. That's in part because gaming the system is associated both with student knowledge and with confusion and boredom. Now you'll note that 3 of these things flip signs from earlier. This is an indicator of how hard it can be to interpret even pretty simple linear regression models. For example, carelessness. Earlier, the students who were more careless went to college more often, but here we see that once we control for student knowledge, they go to college less often. And confusion and boredom also flip signs. The implications? Carelessness is bad, but only once we take knowledge into account. Turns out that carelessness is the disengaged behavior of generally successful students. And this is something that Clements was talking about as long ago as 3 decades, and here we have some evidence. Once you control for what students know, carelessness actually is a bad thing. Boredom isn't a major problem among knowledgeable students. When unsuccessful bored students are removed, all that may remain are those who become bored because the math may be too easy. This doesn't mean that boredom is a good thing. Boredom was still associated with less college attendance in itself. Also, as I mentioned, gaming the system drops out of the model. Now, gaming substantially hurts learning, and this is a well-known phenomenon. Just because gaming to dropout is likely mediated by learning doesn't mean that gaming doesn't matter. In fact, it had the largest effect of any single feature model, a 0.34 standard deviation effect. Another implication is that off-task behavior is not such a big deal, which is interesting because a lot of effort goes into stopping it. My lab does field observation as well as data mining, and one of the things we've seen in our 1,000 to 2,000 or so hours of field observation is that teachers spend lots of time trying to keep students from going off task. And yet, it doesn't seem to be associated with who goes to college, and past meta-analyses find small significant effects on short-term measures of learning, but they're small. I think the meta-analytic summary was like a correlation of 0.1. More so, this doesn't even seem to occur when collaborative learning is occurring, because folks like Cranes have found that when collaborative learning is occurring, off-task behavior can actually promote positive relationships and improve learning. So one implication of all this is that in-the-moment interventions provided by the software, or suggested by the software to teachers, may have unexpectedly large effects if they address boredom, confusion, carelessness in a gaming system. In the next lecture, we're going to go down a different path, and we're going to talk about some less conservative classification algorithms. Should be exciting. See you next time.